Grigory Andreychev, who will tell us about K-theory and dualizable categories.
Okay, thanks. So unfortunately, I have to tell you that unlike the previous talk, I think my talk is not going to be accessible to most of you in the mathematical sense that I think you won't be able to, understand every single definition. It's not that you're going to be able to follow like every step. So what I want to do instead, I want to if you get the vibe of the mathematics that I'm talking about, and I'm going to present a very nice, exciting development in the theory of K-theory. And yes, so let's start. So what is K-theory? So the idea is very simple. So you want to study spaces by analyzing the category of vector bundles. And so like the space can be whatever you want. It can be an algebraic variety, or it can be a topological space, or it can be C-star algebra, or whatever. So, but the main idea is this. You take a space and you analyze the category of vector bundles. So you want to produce a sort of like a series of algebraic invariants, and then you want to control this thing. So let me give you the following definition. So let X be a compact space, so in some sense, and let's denote like by vector C and X the associated category of vector bundles in it. So now I define the group K0 of X as the group completion of the monoid of isomorphism classes of vector bundles in X. So maybe I need to say like what I mean by this like group completion procedure. It's basically the same thing what you do to the natural numbers, to the set of natural numbers to get Z. So you kind of like, you have a monoid, you can add things, but it's not a group, so you formally add formal inverses. Okay, so what kinds of K-theory do we have? So this is already what I mentioned. So you have logical K-theory actually with two different flavors. You have algebraic K-theory and operator K-theory. Let me give you some examples. I think it's going to be maybe like the only examples in this talk. So you can compute the K0 group of the two-dimensional sphere. And so it's actually generated by two guys. So like first of all, you take the trivial bundle on CP1. So like now I view S2 as CP1. So the trivial one-dimensional complex vector bundle, and you have the tautological bundle on CP1. So these two generate this additive group. So if you have a Dedekind domain, then like you know that you can associate this thing called class group of its field of fractions, and this group K0 actually contains this information. And so now, like, let's go to C-star algebra. So here, like, consider the algebra of compact operators on a separable Hilbert space. So actually here, I need to sort of like tweak the definition because this is not a unital algebra. And sort of like in the previous slide, I told you like, consider compact spaces. So this is like, where I need to sort of do something with the definition. But if you do it, then you will see that K0 of like this algebra is actually Z. Okay, so now so like for the rest of the talk, I'm going to talk only about algebraic K-theory because this is what I do. So now let R be commutative unital ring. So, and in the rest of the talk, R is always a commutable unital ring. So is it possible to produce an abelian group for every I? So this like notation K0 suggests that I want a series of invariants, not just one invariant, such that I have this following non-exact sequence. So maybe if you see it for the first time in your life, you're like, okay, like why? So, but maybe for those of you who know a little bit about K-theory, I can say this sequence kind of comes like from descent. Namely, you take the projective one-dimensional projective space over R, and it's sort of like covered by two like affine subspaces, and you also like expect like that the K-theory of like this P1 is actually related to the K-theory of R in a very nice way. So yeah, and then like you can expect such a sequence, and so the answer is yes, you can construct such a series of invariants. And so like let's focus on the negative part at the bottom of the page now. So the negative part is very easy to define. You just like take the sequence and say, okay, like I have K0, so I can define K-1 and so on. But the positive part is a little bit more tricky, and so this is actually one of the main theorems like of Quillen that you can actually do that. Okay, so now I presented some definition, so like maybe let me go back to the slide. So like there is like some construction, BGLR plus. So I don't want to explain what it is, but it's some sort of like topological construction if you wish. So now I want to give a more categorical definition, and there is several reasons why you would want to do that. And one of the reasons is maybe, okay, so let's focus on connective K-theory. So now instead of working with one group, I want to work with a space. So let's look at the space, K0 times BGLR plus. So this thing suggests a very obvious way to make it functorial. You want to, for every map of rings from R to S, you want to have a corresponding map between K of R to K of S. And this formula suggests something wrong. So like the way you would do it, you would consider the induced map on K0 of R to K0 of S, and then like something induced on the right-hand side. But this is actually not what you want, because you want to produce an invariant which satisfies descent. So descent is basically this idea in mathematics. If you have a geometric object and you cut it into two pieces, you want to be able to recover the information on the kind of on the big thing by knowing like what happens on the smaller things and maybe on their intersection. So yeah, if you take this definition above and you insist that you want to consider this map induced like for every map of rings, then you will end up with something which does not satisfy descent, because if it were to satisfy descent, then K0 would, but then, you know, one of the reasons maybe to study higher K groups is actually because you know that this is not true. Okay, so now let me introduce the following like notation. So now I take the groupoid of finite projective modules over my ring R, and I denote it by this like proj R thing. And it's a commutative monoid with respect to direct sums in a very strict, there is a way to make sense of it. I can actually make it a definition. It's not just some like abstract, whatever. So now I want to give the following definition. So I want to sort of make an analogous definition to K0, but now I want to use some sort of topological machinery that I hide. And so now I say the connective K-theory spectrum, K of R, is defined as the infinity group completion of the monoid proj R. So what is going on here? So what does the spectrum mean? So the spectrum is kind of a topological analog of abelian groups. So you may think of it the following way, because like I'm going to talk about connective spectrum right now. So you may think of it as abelian groups in the category of spaces. And so actually, if you define everything in what I just said, it's literally it's a theorem that connective spectra are exactly that. So what you will have like a topological object. So it means like you will be able to consider its homotopy groups. And you will also have like this topological object with some like group structure in it. So for example, the group structure on K0, which will be recovered as pi 0 of this like K of R, it's going to come from this group structure on K of R. So it's not going to be a structure on the set K0. It's going to come like, from something more abstract. Okay, now this problem with functoriality disappears. So because now you can actually produce this map from KR to K of S by saying, okay, so whatever this infinity group completion procedure does, it should be functorial. And so this is what happens here. Okay, and so now, so I want to explain, okay, so we started with something very basic. Was like, okay, you give me a ring, you consider its vector bundles on spec of R, and now I said, okay, like you need to consider infinity group completion. I want to make one step in a more abstract direction again, which I'm not sure if I'm able to motivate it completely, but the motivation is the following. So suppose that you give me a map of rings like R to S, which is, let's say, an open, like corresponds to an open inclusion. Can you actually describe the fiber of this map? So like, this is not a crazy question. Like in topology, this is what you do anyway. Like if you say, okay, like I give you space and you want to compute a singular homology, let's say. Like if you just give me the definition of the space and the definition of singular homology, the task to compute it directly is kind of an absolutely crazy thing to do. So you want instead like to do like some geometric procedures, you want to cut your space, you want like, to have like some excision or whatever, and then you're going to be able to end up with an answer. And so this is what we are trying to do here, but the problem is that if you want to analyze the fiber of this map, you cannot actually describe it as K-theory of any ring. So there is like some geometry missing. And category theory here comes in and helps us. So because it will introduce this missing geometry, it will introduce a category which will like yield this fiber. Okay, so what we're gonna do here, we're gonna introduce this category proof of R. So now you may think of it as finite complexes with finite projective terms and up to like, quasi-isomorphisms and so on. And so basically, instead of working with proj of R, which was just finite projective modules, now you work with finite complexes of those. So if you know about homological algebra, this is a very natural thing to do. And so now you can look at this functor, perf of R to perf of S, which is the base change functor. You take a complex, you tensor it with like S, and then you get a complex over S. And so you consider it's fiber. So what is a fiber? So it's just basically all objects that map to 0. So for example, if R is Z and S, I don't know, like Z inverted 2, a guy which gets killed by this procedure would be Z mapping to Z multiplied by 2. So like F2 basic would be killed. Okay, so now the point is that, so now you can construct this world of categories called, so here is like some adjectives. I don't want to explain what they are. Let's call them nice categories. So like small item home, complete, stable, infinity categories are going to be nice categories today. And so there is 2 examples maybe that you want to care about, like so the category that I just introduced, infinite type spectra. And now there is a theorem that there is a functor from this world of categories to the world of spectra, so this world of new topological abelian groups, which satisfies a certain universal property. And if I explain to you what this universal property is, it is extremely confusing because it's basically like the most simple thing you can think of. Like you just say, okay, you take a category, you apply the square functor, which is the most simple thing you can think of if you want to take a category and produce a spectrum. And then you force it to be localizing. Okay, so now you can apply this functor to the fiber between these 2 categories. Again, like this is going to be a category which does not really correspond to a ring, but it lives in this world of categories. And suddenly all the proofs that you wanted to have, they work. Before that, it was like no one could prove anything, but now seems like almost like a formal thing to do. You just like introduce like some virtual objects which do not correspond to any ring, but actually it works. Okay, and maybe, so now I want to say, this is actually not enough either. So for example, So take this category of nice categories, and it turns out it does not contain all necessary fibers. So let me formulate it like this. So there exists a bigger category of dualizable stable infinity categories, which contains this category of nice categories. And its objects can be thought of as formal differences of objects in the world of nice categories. So if you wish, you can call them like virtual nice categories, analogous to virtual vector bundles. So it's kind of formal differences. And now, yeah, so like the rigorous mathematical definition of this is that every dualizable category C sits in a short exact sequence like C, D, E, where D and E are nice. Okay, and there is a theorem, you can actually extend the functor from the K-theory functor from this world of nice categories to the world of dualizable categories. Okay, so maybe before I continue and go to the last slide, I want to stress something. So I just introduced these gadgets as like some formal differences of nice categories. Maybe one of the points is that actually, yes, it's one way to think about them, but they are also actual categories, which is great. Because once you know that this is a definition that you care about and you start looking for it, you see them everywhere. So for example, if you take a locally compact Hausdorff space X and you just consider sheaves of spectra on this space, well, it's not compactly generated in general, but it's dualizable. You can prove that the category of almost modules, so if you care about like number theory, or I don't know if you care about algebraic geometry, the category of almost modules is also dualizable. Now you maybe know about condensed mathematics and you heard like that there is like exciting developments there. So the category of nuclear modules over something like QP, so it carries some topology, is also dualizable. Now let's go back to this C star example that I gave. So we can define the K-theory of the algebra of compact operators on a Hilbert space H. So I just explained that like the point is you want to define it not just like some random construction in some field of mathematics. You want to be able to do the following. You give me an object, I produce a category, and then there is a way to assign K-theory to every category, which doesn't know anything about where you are coming from. So here is the construction. So you take the direct category of the algebra of bounded operators on your Hilbert space, consider this functor, take its fiber, and this is a category, this is a dualizable category, and you can take its K-theory. And maybe the final example, so maybe you also heard that in the world of condensed mathematics, people are able now to define so-called liquid modules. So this is some theory over C. So like this is a category of string modules over C if you wish. And this is a dualizable category again. So maybe I should say actually strongly nuclear liquid modules or something like that. And now you can take its K-theory, for example. So the point is that like a lot of very different constructions, which actually come from the same idea of K-theory, now end up in the same world of category theory, and you can study them with the same tools. Thank you.
Questions to the speaker? Yes.
In your previous slide, where does the Schrodinger's sequence take place?
In parallel, let's say. Yeah.
And it would cover algebraic K-theory from this machinery?
Yeah. So this is like actually, I mean, what I tried to say here is basically it kind of this thing helps you start to study other K-theories as well, but what do I do now? Okay, so what I was trying to explain like somewhere before, I don't know, like slide 8 or something like that. The motivation to do that actually comes like from algebraic geometry. So that was like where people realized, okay, so the algebraic K-theory of a ring will be the algebraic K-theory of the category of perfect complexes, like over this ring. So this is like, you know, when people realize, oh, like we need categories. And what I was like trying to say before that, sorry, that was not really like, you know, clear. People realize that there are questions there where you have like a map between two rings and you want to study like an invariant which pops out like when you just consider the fiber. It does not correspond to anything algebraic in the sense it doesn't come from a ring, but it will come from a category. And so this is like where people start caring, when people started like, you know, working with categories and so on, and then they realize, oh, actually you can apply this machinery pretty much everywhere.
Okay, I think we should start setting up for the next stop. So we just thank Greg again.